Welcome to the first in a series of demonstrations by XIO Technologies. My name is Hollis Beal, and I'm the Technical Director for the Cloud Business Group. The XIO Intelligent Storage element is designed for environments that have high performance requirements while at the same time have high capacity requirements. This would be environments where they have so much data that they can't afford the number of SSDs it would take to store it all, but at the same time the performance requirements are so high that they couldn't afford the number of hard drives it would take to get the performance that they need. The ISE is a 3U enclosure that's been designed with no single point of failure and no common mode failure. With active-active controllers, hot swap modules, and mirrored power-redundant cache, the ISE 7 series uses 30 hard drives and 10 SSDs to get the performance of SSD with the capacity of HDDs. The ISE can be directly plugged into a server or into a fiber channel switched infrastructure. This test is going to be run with a single ISE 720 hybrid storage system. By using a patented tiering algorithm called continuous adaptive data placement, hot blocks of data are migrated to SSD in near real time. This means that the ISE can take advantage of the hotspots that develop as a LUN is used. CADP automatically moves these blocks in near real time to the SSDs, giving these blocks the SSD performance they need. The ISE has some of the highest percentages of SSD capacities available, between 7 to 22%, to accommodate varying amounts of hot data. There are other hybrid solutions out there that utilize SATA or nearline SAS technologies to increase the effective capacity, but there's a pretty big penalty for this in terms of reliability and performance. So don't be fooled. At some point, that data has got to get back to the hard drives, and this is where using enterprise hard drives are really important, and in this video, I'm going to show you why. For the hard drives, the ISE only uses enterprise SAS disks, which we can make run 2 to 3 times faster than the same drive in anyone else's array. This gives the ISE a faster, more reliable base for all of the data that's not going to be an SSD. In this video, we're going to show how these things combine to give the ISE superior performance with one of the most challenging workloads out there. Today, I'm going to show you what it looks like to boot 1,000 VMware linked clones from a single ISE 7 series storage system. Virtual desktop environments are an excellent use case for the ISE technology, and one of the most performance-demanding operations these environments encounter is the bootstorm. This operation puts a tremendous strain on the underlying storage system, so we're going to use this as a tool for demonstrating performance. The environment was configured with 2 HP DL585 Generation 7 servers. Each of these have 64 cores and half a terabyte of RAM, and there are no internal SSDs. These servers were directly connected to an ISE 720 hybrid storage system with a QLogic dual-ported HBA. Alternatively, the servers and storage could have been connected with a fiber channel switch, as the ISE supports both connection methods. Both servers were installed with VMware 5.1, and vSphere DRS was set to aggressive to balance the VMs between the servers. The ISE also implements the VMware VAAI functions, so we didn't have to do any out-of-the-box tuning for storage. Things like HPA driver queue depth and other VMware advanced disk settings are automatically handled by the API. We created 10 LUNs on the ISE and attached each of them to a VMware data store using the ISE Virtual View plugin for the vSphere client. Using Virtual View made configuration of the environment a lot easier because Virtual View handles the entire storage provisioning process from end to end, and it saved a ton of time. Each data store contained a base image and 100 linked clones of that image. We created this test process with the idea that we wanted it to be easy to replicate, so that if you watching the video has a lab to experiment with, it would be relatively simple to recreate the test in your environment. We're going to start out with a single Windows 7 32-bit base image. Then we're going to create 10 clones of the original, with each base image getting its own data store. We take snapshots of the base images and then use the VMware API to create 100 linked clones from each base image for a total of 1,000 VMs. Once the linked clones are created, all of the virtual machines are started to observe the demand on the storage system. In doing this demo, we again use the XIO Virtual View Management plugin for vSphere to start all the VMs. Alternatively, you could use the vSphere client or scripting to start the virtual machines, but I found that I could start more VMs at a time with the Virtual View plugin, which produced more load on the storage system. The advantage of using a bootstorm as a method to stress test performance is that it's fairly easy to set up and all steps can be accomplished in a relatively short period of time. In this video, we're going to observe the response of the ISE during all phases of this process. In this video, we're going to be using the ISE Performance Adapter for Windows Performance Monitor to view detailed metrics of the ISE system. The ISE Performance Adapter is simply installed on a Windows VM that has Ethernet connectivity with the ISE. And you are seeing 3 instances of perfmon open on the screen to show various aspects of the ISE's performance. There is a statistics view of the main ISE metrics, showing instant values for total read and write latencies, total throughput, and total IOPS, and this allows for you to see exactly what the value is of any of these metrics when we slow down and take a look at what's going on. Then there is a graph of the total ISE system metrics, and this allows you to see how these values are changing over time as we move through the test. The last perfmon instance is a graph of the total backend I/O going on to each physical SSD and HDD in the system, with all 40 devices on the same graph. Now in this, I've colored the SSDs blue and the HDDs green so you can see where the performance demands are. All the graphs have a 16-minute display interval and are stacked on top of each other so you can see how the backend activity corresponds to the total ISE system performance. And lastly, we're going to have a timer running to show where we are in the test, which in total runs for about 2 hours and 40 minutes. Now keep in mind the typical speeds for estimating performance of different disk drives. Usually we can say that a SATA drive will do between 85 to 100 IOPS, a 10K RPM disk drive can do about 125 to 150 IOPS, and let's say a 15K RPM disk can do about 200 IOPS. The first thing we're going to do is to create the 10 base images from the initial image, and we're going to use Power CLI to automate the creation of these clones. What you're seeing here is the effect of the VMware API for the copy offload functionality. Now we're halfway through the clone process and there's hardly any front-end activity on the ISE. But if we look at the back-end SSDs and HDDs, we can see that there's a lot going on. So we're seeing total IOP values on the individual hard drives reach about 600 IOPS per drive. Now, one thing to keep in mind, that the more you do these kinds of deploy operations, this is going to reduce the reliability of lesser duty cycle drives. So if you're planning on doing this with any kind of SATA technology, there's going to be a problem sooner rather than later when they have to put up with this kind of workload. So this is one operation where having enterprise hard drives for the reliability and getting them to run 2 to 3 times faster is a tremendous advantage for the ISE. We completed the clone process in a little over 3.5 minutes, copying 100 gigs of data. Now that the base images have been created, we're going to take snapshots and then use the VMware API to create the 1000-link clones. One surprising thing in this test was the performance required for this operation. We're seeing front-end IOPS on the ISE have regular spikes to 5,000 IOPS, and this goes on for about 13 minutes total. And notice while this is happening, our read and write latency are mostly 0 so far. Now that we have the 100 link clones created, it's time to do the bootstorm. We use the XIO Virtual View Management plugin for the vSphere client to start the VMs, but you can also use the vSphere client to start them as well. Now, several storage systems offer vSphere integration, so I encourage you to utilize that in your testing to evaluate it. When we start all the VMs, the processor utilization on the 2 DL585s goes to 100% and stays there for pretty much the entire duration of the bootstorm. This was not meant to be a test of how fast we can boot 1,000 VMs, as the servers are being pushed well past what they can do and are the main limiting factor in the test. We are just using the bootstorm to show how the ISE responds to the demand of this operation. We can see that the IOPS in the ISE are getting past 40,000, and we can also see that the read and write latencies have been below 10 milliseconds since the start of the test. Now at the high, the ISE was doing about 1.4 gigabytes a second in throughput, with the majority of this workload being 75% or higher of reads. We can also see the IOPS of the SSDs increasing over time, showing that C80P is moving the hot blocks up to SSD, while the individual hard drives are now doing between 200 to 500 IOPS apiece. Now, this is another reason why having enterprise-class hard drives are important in any kind of hybrid storage design, because these disks have to support I/O demands for the vast majority of the capacity in the solution. After 45 minutes, the bootstorm is over. Now, during this process, we saw the front-end performance on the ISE reach between 30,000 and 40,000 IOPS, with read latency values under 20 milliseconds and write latency values under 10 milliseconds for the duration of the bootstorm. This shows that the ISE was able to accommodate the workload without any indications of any performance problems. The processor utilization on the ESX servers have come down from 90 to 100% utilization to about 40% utilization now, and the boot phase appears to be over. At this point, there's a significant change in the workload. Now, what we're going to see in the next part is a dramatic increase in the amount of write I/O to the environment and an overall increase in IOPS from the ISE, with 1,000 virtual machines just sitting there being idle. We can see the IOP level on the ISE is staying around 50,000 IOPS, but 75% of these are writes. So right now, the ISE is doing over 30,000 IOPS of writes, while our write latency is around 15 milliseconds. So as you have seen, the ISE can handle one of the most demanding operations that a VDI environment can require. You've also seen how the ISE's C80P algorithm can dramatically increase the array performance by moving hot data from the hard drives to the SSDs in near real time. And finally, you hopefully will have a better understanding of the importance of using enterprise hard drives in any hybrid array, and how important the performance and reliability of these devices are in this architecture. Thank you for your time to view this demonstration. For more information, please visit our website at www.x-io.com or email us at fastforever@x-io.com.